Okay, so in this section, we're going to use what we call numerical integration to be able to compute difficult integrals. So we're going to approximate the value of a definite integral by using the midpoint trapezoidal rules, and then we will also then do the Simpson's rule, determine the absolute relative error in using these methods, estimate the absolute relative error using the error-bound formulas, and recognize which ones are better and which ones give you overestimates and underestimates. So as we look at these are some difficult integrals: e to the x squared, integral of dx over x cubed plus 4, and the integral of log of x squared. So the three methods that we're going to do are the midpoint rule, the trapezoidal rule, and the Simpson's rule, and all of them are going to help us approximate what we call the definite integral. That means we are able to approximate it on an interval, so we know where it starts and it ends. And the definite integral is nothing more than the area under the curve of a function f of x on the interval AB. Okay, so the first thing we're going to do is the midpoint rule. And so this is how the midpoint rule works. I just dropped my pen. Okay. This is how the midpoint rule works. So say we have a function. So here's my graph here. And I have a function floating over top, whatever it looks like. Okay. And then we're going to take this function, and what we want to do is this is the integral from A to B. And so we want to divide it up into n equal sections. Let's say for this one, we have 6. So we have n subintervals. And the length of each subinterval we're going to call delta x. So that's the length of any subinterval. So that would be like from here to here. So that is delta x. And delta x is simply taking the length of the interval b minus a and dividing it by n. So if the interval happened to be 4 units and we have 6 intervals, then it would be 4 over 6 or 2/3. Okay, so we're going to do that. And then what we do is we're going to take and we're going to find, all right, so each one of these intervals, we split the function for each one of these intervals as such. And we are going to approximate rectangles on each interval. Okay, so what we're going to do is the integral equal to the integral from A to B of f of x dx is going to be approximated by the sum of n areas. All right, so the area is going to be calculated as follows. On each interval, you are going to find a midpoint. So this one would be M1. This one would be M2. This one would be M, n minus 1. And this last one would be Mn. So we have n of those, and we find the midpoint. So we would take the interval from A to B, divide it up into your n units, and then find the midpoint. So this would be M1, M2, in this case, M3, M4, here M5, and M6 for this example. So you have those, and then you go up as high as you can to find f of M1. So now that I have f of M1, I am going to draw a rectangle the height of f of M1 I'm going to go all the way up to M2, and I am going to draw a rectangle whose height is M2. Here's M3, so I'm going to go all the way up to M3 and draw a rectangle the height of M3, go all the way up to M4 and draw a rectangle the height of M4. Here's Mn minus 1, so that would be there. Draw a rectangle that height. And then this being the last one, I would draw a rectangle of that height. So now I need to find the area of each one of these rectangles. Okay, so the area of each rectangle, that's easy to find. So, I want that to be a different color. Oh, come on now. Yeah, I want that to be a different color. So each rectangle has its own area. And it's easy to find the area of each rectangle. So we're going to sum up all these rectangles. And in the essence of time, I am not going to color in the last three because this is not a coloring project. Okay, so we're going to sum up all the areas. So what is this? So the area of the first triangle, of the first rectangle, A1, is simply, well, it's the height, F of M1 times the length, which is delta X. And the area of the second one is F of M2, that's the height, times the length, which is delta X. And so we keep doing this and we find out the area of the last one is F of Mn times the height, which is delta X. Okay. So therefore, our if we sum them up, that's going to be our approximation of the integral. So we get the integral from A to B of f of x dx is going to be approximately the sum A1 plus A2 all the way up to AN. Okay. So that is approximately, that's equal to, so now I can use equal to F of M1 times delta X plus F of M2 times delta X all the way over to F of Mn times delta X. So if I factor out the delta X, I can get a sum. So I get delta X times the sum, K equals 1 to N of F of MK. All right, so this I am going to call the midpoint approximation MN. So M stands for midpoint and N is the number of intervals. So M stands for the midpoint rule. And N is the number of intervals. Now, the more intervals you divide it into, the better the solution. Okay, the more intervals you divide it in, the better the solution. So where's my formula? There it is. All right, so the integral from f of x dx is approximately Mn. Mn is, as we said, delta x, the sum k equals 1 to m of the f times the midpoints. And remember, delta x is b minus a over n. So that's the formula. All right, so here's our first example. Okay, so here's example 1. And example 1 says compute the integral from 0 to 3 of x cubed dx. N is 4. Okay, so I'm going to take and delta x then, which is b minus a over n, is going to be 3 minus 0 over 4. So delta x is 3/4. Let me draw my interval here. So n is 4. So this is 0. This is 3/4. This is 6/4. This is 9/4. And this is 12/4, which we automatically know as 3. Now, I like to do it where they all have the same denominator. So instead of doing 3/2 here, I left it to be 6/4, and you'll see the reason why. So if I have 0 to 3/4, then I add 3/4 to the next one, gives me 6/4. I add 3/4 to the next one, gives me 9/4, and then I get the 3. Okay, so that's my interval. Now I need to find my midpoints. So I need M1, I need M2, I need M3, and I need M4. Okay, so how do I find M1? Well, M1 is just half the distance between 0 and 3/4. So therefore M1 is just 3/8. Okay, so M1 is 3/8. And then I'm going to add 3/4 to it. Okay, so I need 3/8 plus 3/4. Well, what is 3/4? That's 3/8 plus 6/8. So when I add 6/8 to this, this becomes 9/8. If I add another 6/8, this becomes 15/8. And another 6/8, this becomes 21/8. I believe that's right. 3/8, add 6, 9, add 6, 15, add 6, 21. I believe that's correct. Okay, so now I know what my M's are. So everything is known. Okay, everything is known. I took my interval, I divided it by 4. I found the midpoint of the interval. I already know what delta x is. So here's my formula. So here's my formula. So M4, so the integral from 0 to 3 of x cubed dx. This is going, oh, I want to make this M4 first. Yeah, that's right. Let me do that. So M4 is delta x times the sum k equal 1 to n of the f of mk's. All right. So that's going to be delta x. And when I sum these, I'm going to get f of m1 plus f of m2 plus f of m3 plus f of m4. Okay, and here for this problem, we need to know that our f of x that we're working with is x cubed, because that's the function here. So my f of x is x cubed. My a and b are 0 and 3. Okay, any questions so far on the setup? Because this is actually not very difficult, but a lot of students make it difficult. Yes.
I just got lost with the numbers. So you're adding your previous M number to.
We're adding f of those numbers. Okay, we haven't found them yet. I'm getting ready to give them to you.
No, I'm talking about the line above.
Okay.
When we're doing like the midpoint.
Yes.
I'm just confused. Like, so that's what I'm saying. For M1, it was half of whatever that was.
Right. So M1, so actually the way you find the midpoint is to take the 2 points, add them together and divide by 2.
Oh, okay, divide by 2.
Okay. So if I take 0 plus 3/4, I get 3/4 divided by 2, it gives me 3/8. If I take 3/4 plus 6/4, that gives me 9/4, divided by 2 gives me 9/8. If I take 6 and 9/4, that gives me 15/4, divided by 2 gives me 15/8. And 9 and 21/4, I'm sorry, 9 and 12/4 gives me 21/4, divided by 2 gives me 21/8. So to find the midpoint between any two, just add them together and divide by 2. Peyton?
Yeah, I understand now.
All righty. Okay, so in the essence of time, I found f of these numbers already. Okay, so here we go. This is how did I find them? Well, f of the first one, if you remember, was 3/8, right? So I'll actually write that out for you. So this is delta x, which was 3/4. And then we're going to have f of 3/8 plus f of 9/8 plus f of 15/8 plus f of 21/8. All right. So in the essence of time, I calculated these already. So f of 3/8 is to take 3/8 squared. Okay, the function is x cubed, I'm sorry, cubed. The function is x cubed. So f of 3/8 is 3 cubed is 27, 8 cubed is 512. So we get 3/4 times 27 over 512. Then we have 9/8 cubed. So that's 729 over 512. Plus 15/8 cubed. Well, that's 3,375 over 512. And then 21 over 8 cubed is 9,261 over 512. Okay, so now the way to do this is easy. If you've done it like this, you can factor out the 512. So this becomes 3 over 4, factor out 1 over 512. And then on the inside, you just get 27 plus 729 plus 3,375 plus 9,261. And then this gives you 3 over 5 times 512 times 4 is 2,048. And that whole thing sums up to 13,392. So if you take that answer and figure out what it is approximately, it comes out to be 19.617. Okay, so that is my approximation to the area under the curve of x cubed. Okay, that's my approximation to the integral. Okay, so now what is the true value? Okay, well, let's see the true value of the integral. So the integral from 0 to 3 of x cubed dx is 1/4 x cubed, x to the 4th, evaluate between 0 and 3, which is 81/4. And that comes out to be 20.25. Okay, so this is the true value. All right, I'm going to put this in a nice red block. So this is the true value, or the exact value. I should call it the exact value. Okay, so that's the exact answer. Okay, so now we can actually compute the error in this answer. All right, so the error, what we're going to call EM. Oh, I think I got something for this. Yeah. Okay, so the error EM is simply to take the I, which is the true value of the integral, thank you. I, which is the true value of the integral, minus M4. So that's the error. The error is how far are you away from the true value? Okay, how far are you really away from it? Okay, so we can calculate that. That's the absolute value of 20.25 minus 19.617. And if I'm using 3-digit arithmetic, that comes out to be 0.633. Now, that's how far we are away. The relative error is a better approximation. It gives you a percentage off of what you really are. So it says to take that value, the absolute value of 20.25 minus 19.617 and divide that by the actual true value. So if I divide that by 20.25 and this, oh, and then multiply this by 100, this actually gives me 3.3, no, 3.13 if you multiply that out. So I'm only off by 3%. That's not bad. That's really not too bad. Okay, now we also can calculate what we call the maximum error bound. Okay, so the maximum error bound tells you the biggest the error can be in this approximation. Okay, so it's basically the biggest the error can be. And so we have a function f, it's continuous, that's x cubed. It's on the closed interval 0, 3. It has a second derivative. So if k is the biggest the second derivative can be on the interval, then we can use that to approximate the maximum error. And here it is. And I'm going to show you how to do this. So we can calculate the maximum error. So in order to find k, we take the second derivative. So f of x is equal to x cubed. F prime of x is equal to 3x squared. And f double prime of x is 6x. Okay. So on the interval 0, 3, the biggest, or the max, I'll say the maximum value of f double prime of x is obviously 6 times 3. That's the biggest it can be, and that's 18. So therefore, we're going to let that equal k. So you find the second derivative, and you make it the biggest it can be on that interval. So the biggest the second derivative can be on that interval is 18. So that's going to be our k. If you remember b minus a, well, that's 3 minus 0. So that's 3, and n was equal to 4. So therefore our EM, okay, that's the maximum error in the midpoint rule, is less than or equal to k, which is 18 b minus a, which is 3 cubed, divided by 24, and n squared is 16. So this comes out to be, I didn't calculate this already, so I'm going to calculate it now. So this is 18 times 3 squared is 27, divided by 24. 24 times 16. Okay, so the biggest the error could be is 1.2, and see, we are way below that error. Okay, our error is 0.63, so we are way below the maximum error bound. All right, so this is the maximum error bound. For the midpoint rule. And notice every problem is going to change. So you're going to have a different error bound for everything. Okay. All right, any questions? I'm going to post the notes if you want to be able to copy that exactly. So if you want to just leave space in your notes, I'm going to post these. Okay. All right, we're going to do the same problem now, but we are going to use the trapezoidal rule. Okay. So the trapezoidal rule is just a wee bit different. The trapezoidal rule is going to be based on finding areas of trapezoids. Okay. So I'm going to draw a picture again. So here is, I don't want that red. I want that black or gray. I don't want that. I want that. Okay, so I'm going to draw another function. So again, we're on the interval AB. And again, delta x is b minus a over n. So we're going to take and divide this up into n equally spaced regions. I've been just using 6 just because it works. Okay, and so now this one is going to count as our first one. So that's going to be x0. That's going to be x1. That's going to be x2. And we're going to count up to, this one will be xn minus 1. And this last one will be xn. Okay, so the difference with this one is now when we divide it up, the first value is x0, this is x1, x2, all the ones in between, xn minus 1, and then xn is the last one. Okay, so this time, instead of making rectangles, out of our midpoints, this time we are going to make trapezoids. Okay, so here, the first one, the first trapezoid actually turns out to really be, for this one, a triangle. But now you can see the trapezoid here for that one. Okay, you can see this trapezoid for that one. You can see that trapezoid for that one. You can see another trapezoid here. And again, this last one turns out to be a triangle. Now, it could be that the function doesn't go down to 0. I should have thought about that. It doesn't have to go to 0. The function could go like that. And if the function goes like that, then obviously this last one would also be a trapezoid. So the function doesn't have to go to 0. I didn't think about that when I drew it. So here's another trapezoid. Okay, so this time now we're going to sum up the areas of the trapezoids. So let's go back for one brief second. We summed up the areas of the rectangles. So this time we're going to sum up areas of trapezoids. So let me just draw, I'm gonna color just a few in just so you can see them. Here's one, give me the green. So there's a trapezoid. So as you can see, we're summing up the areas of the trapezoids. Okay, here's another. Okay, so what's the area of a trapezoid? Well, the area of a trapezoid is 1/2. You need the first base plus the second base times the height. So if I have a trapezoid that looks like this, I don't know if this is going to do this right. Oh, let's try it again. Yay. Okay, that's not too bad. All right, so there's my trapezoid. So the height is this length right here. So this for us is going to be our height. This is going to be base 1, base 2. So the area of that trapezoid is to take 1/2 the base, the sum of the bases times the height. All right, so just for this one trapezoid, that means the area is going to be 1/2. Well, the first number, this height, maybe is f of x k minus 1 plus the height of the next one, f of xk, and then times the distance we said here, or that distance, should put there instead. That is delta x. Okay, so that's just one of them. So let's see what happens if we sum a bunch of them. So we get the area is going to be, well, we have 1/2 f of x0 plus f of x1 times delta x. So that's the first one. The next one will be 1/2 f of x1 plus f of x2 times delta x. And we're going to keep doing that all the way to the end, which is going to be 1/2 f of xk minus 1 plus f of xk times delta x. Hi, babe. Okay, so then the area, what can we pull out? Well, we can pull out the delta x and we can pull out the 2. So from this first one, I'm going to get f of x0 plus f of x1. From the next one, I'm going to get f of x1 plus f of x2. From the next one, I'm going to get f of x2 plus f of x3. So I hope you guys are catching on now. All the way up to the last one, where I'm going to get f of xk minus 1 plus f of xk minus 1 plus f of xk. And that's how we get the trapezoidal rule. So the trapezoidal rule Tn is delta x over 2. You get 1 of the first one, f of x0, but you get 2 of the next one, f of x1. Then you get 2, oh my goodness, what in the world is going on? Stop it. Okay, it's decided it wants to behave, not behave. Plus 2, now we have these, we have 2 of these. So notice all the inside terms we have 2 of. 2f of x1, x2, all the way down to 2 times f of xn minus 1 plus only 1 of the last one. And that is our formula. So here's my trapezoidal rule. So the integral is approximated by Tn, which sums, takes delta x over 2, sums every f evaluated at each one of the endpoints where you get 1 of the first one, 1 of the last one, and 2 of all the ones in between, where delta x is b minus a over n. Okay, any questions? The derivation is a little, but if you can remember the formula, yeah, yes. If you can remember the formula, then it'll work for you. Okay, so here's the problem, same problem. Same problem. Integral from 0 to 3 of x cubed dx, and n is 4. So that again, yep, I have a question. No, this is not on the exam. No, 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 no. This is not on Thursday's exam. Delta x, again, is b minus a over n. So that's going to be 3 minus 0 over 4. So again, delta x is 3/4. Okay, so therefore now, I have this. Remember, I divided this up into 4. So this is 0. This one was 3/4. This one was 6/4. This one was 9/4. And this one was 12/4, which again, we said was 3. Okay. Okay. So therefore, T4, which is the approximation to the same integral that we did with the midpoint rule, is going to be delta x over 2. So delta x is 3/4 divided by 2. We're going to have f of 0 plus 2 times f of 3/4. Notice I'm not using the midpoints. I'm using the endpoints. Plus 2 times f, of 6/4 plus 2 times f of 9/4. And then only 1 f of 12/4. Okay, any questions? So we're just using the trapezoid rule now. All right, so I took the liberty to calculate these ahead of time. So now we know what each one is. So T4 looks like 3/8. F of 0 is 0. Plus 2 times f of 3/4 is 27 over 64. Plus 2 times f of 6/4 is 216 over 64. Plus 2 times f of 9/4, which is 729 over 64, plus 1 f of 12, which is 1,728 over 64. Okay. So I can very conveniently, again, I like doing it this way because I have the same common denominator. Okay. So I can, that's the wrong problem. Where's the Simpsons rule? I mean, Yeah. Oh, I think I divided 2 out of everything since I saw everything was divisible by 2. So I made it easier for me. I divided everything by 2. So I made this 27 over 32 plus 216 over 32 plus 729 over 32 plus 1,007, no, 864 over 32. So then I factored the 32 out. So I got 3 over 8 times 1 over 32. And that left 27 plus 216 plus 729 plus 864. And that came out to be, why didn't I do that? I didn't feel like it. $5,508 divided by 256. And if you do, that's approximately 21.516. Okay. So before, when we did the midpoint rule, we got 19.617. Have we done already? Yeah, sit it right behind me, please. Thank you. Okay, we already calculated the true value. All right, so now we can find the error in the trapezoidal rule. Okay. So the error in the trapezoidal rule is to take the absolute value of the true value, which is 20.25, and subtract off 21.516. And that value comes out to be 1.266. And so then the relative error is to take that 20.25 minus 21.516, divide that by the true value, 20.25, and then multiply it by 100. And that is equal to 6.25%. So for this particular problem, the midpoint rule gave a better approximation. Okay, because the error for the midpoint rule was smaller, remember? Okay. Give you a minute to get that down. Okay. So just like the midpoint rule, we have an error bound for the trapezoidal rule. And the error bound for the trapezoidal rule is just like similar to the error bound for the midpoint rule. It also depends on the second derivative. So it depends on the second derivative, and its error bound is like this. Yeah. So it almost looks identical to the error bound for the midpoint rule. I think the difference is a factor of 2. So here, this one was divided by 24, as you can see here. This one was divided by 24. And this one is divided by 12. Okay, so you can calculate the maximum error for the trapezoidal rule as well. Okay, any questions? Because I have one more rule to give you guys. And this one I'm not going to derive. This one, I'm just going to give it to you, because it is a beast to derive. Any questions? Okay. All right, so the last one is Simpson's rule. All right, so for Simpson's rule, here's the big deal. N must be even. You cannot use Simpson's rule if N is not even. It does not work. Again, delta X is equal to B minus A over N. That's still the same. And so Simpson's rule is as follows. Here is Simpson's rule. Okay, so the difference with Simpson's rule is that for Simpson's rule, not all the values are multiplied by 1. Not all the values are multiplied by 2. First off, notice that it is delta X over 3. The trapezoidal rule was delta X over 2. And remember, the first and the last element appeared to only one time, and everything in the middle appeared twice. Okay, for Simpson's rule, again, N must be even. We have delta X over 3. The first element and the last element appear once. F of X naught, F of Xn. But in between, they alternate. The next one is multiplied by 4, then the next one's multiplied by 2. The next one's multiplied by 4, then the next one is multiplied by 2. And we do this all the way to the end. The second to the last one is multiplied by 4. And then again, the last one appears by itself. So let's do the problem. Same interval. Okay, so now we're going to do the same integral, and this time we're going to do Simpson's rule. All right, so Simpson's rule says we're going to do n is equal to 4. Delta x is going to be b minus a over n, which again is 3/4. Then we still have the same picture here. Because it's the same interval. Okay. And we still have the same values. Okay, so make a note for Simpson's rule and trapezoidal rule, you will use the same points. For the midpoint rule, remember, you use the points in between. Okay. So S4 is going to be 3/4. Whoops, what in the world is that? Divided by 3. We're going to get f of 0 plus 4 times f of 3/4 plus 2 times f of 6/4 plus 4 times f of 9/4 plus 1 times f of 12/4. Okay, so can you, I hope I'll give you a minute to catch up on that. So I get 1/4. F of 0 is 0 plus 4 times 27/64 plus 2 times 216/64 plus 4 times 729/64 plus 1 times 1,728/64. Okay. So this is going to be 1/4. Factor out the 1/64. And you get oh, I added it all up already. I got 5,184. And guess what? This turns out to be 20.25. So this one happens to be exact. Okay, so the question is, why is it exact? Is it always exact? Well, the answer is no, it is not always exact. So here the error, did I write that out? Yeah. Okay, so for this problem, the error turns out to be 0. And so does this. And here's the reason why. Okay, so we have a maximum error bound for this. But this one depends on the fourth derivative. So for this one, k is the fourth derivative. And not only is k the fourth derivative, the error goes like the maximum error in Sn turns out to be smaller than k, which is the maximum of the fourth derivative, times b minus a to the fifth over 180 n to the fourth. Okay, so for this problem, if you remember, we said f of x was x cubed, f prime of x was 3x squared, f double prime of x is 6x, f triple prime of x is 6. And so the fourth derivative at x is 0. So that's our k. So that's why this for that problem was 0. Okay, I'm going to take roll, and then when I come back from taking roll, some of you are thinking, okay, what am I supposed to do with this on my homework and on the test? Okay. All right, so what you would do is on your homework, you would use your calculator and round to the nearest requested decimal point. So on the homework, it's going to say, put in, find, it'll give you a problem. So the homework will give you something like find or estimate. It'll say something like estimate the integral from 0 to pi of the cosine of x squared dx. So it'll give you something like that. Okay. For M4, T4, and S4, or M6, T6. Some of them are awful. I've had students that I've worked with who had to do T10. I said, your professor's mean, give you T10. Okay, so, but you may have whatever the number is. It may be M5 or something like that. So then you would divide your interval. Okay, so you would just do what we did. divide your interval. So you may have 0, pi, this would be pi over 2. So this is pi over 4. Pi over 2, you could do 2 pi over, and then this is 3 pi over 4, and then pi. So you have that. So of course, for your midpoint rule, you'd have to use pi over 8. And then this is actually 3 pi over 4. So it's easier for me to see that as 2 pi over 4. So then this would be 3 pi over 8. And then this would be 5 pi over 8. And then this would be 7 pi over 8. Okay, so therefore for your midpoint rule, you'd use the ones in red. And for your trapezoid and Simpson's rule, you'd use the ones at the bottom. And then you would do it. And then you would take the calculator and calculate all that stuff. And then it's going to say, put your answer into the 4th decimal place or something like that. And that's what you would put in. Okay, so it may say, like I said, to the 4th decimal place or whatever, you go ahead and put it in. On the exam, you will not have calculators. So on the exam, since we don't have calculators, what do? All right, so here's an example. Calculate the integral from 1 to 4 of e to the negative x squared dx, and n is equal to 6. Okay, so on the calculator, on the test, I would take and get delta x is b minus a, which is 4 minus 1 over 6. So that's 3/6, which would be 1/2. I have a comment in the chat. 3.6, this is not on the exam. The exam covers 3.1, 3.2, 3.3, and 3.4. 2 problems from each section. Okay. Then you would take your interval. So this is 1 and this is 4. And I got to divide it up into 6. And each one is a half. So therefore, this would be 3 halves, 4 halves. If you want to just do 2, since you're doing it on the exam, it doesn't matter. You're not going to have a calculator. 2, and this would be 5 halves, and this would be 3, and this would be 7 halves, and that would be 4. Okay, so for your, let's see, which one did I calculate? Trapezoidal rule. So on the exam, the answer that will get you full credit will be this. T6 would be b delta x over 2, so that's 1/4. Then I would have the first one, which would be e to the negative 1, because that is 1 squared. Trapezoidal rule, plus 2 times the second one, which would be e to the negative 3/2 squared, so that would be negative 9/4, plus 2 times the next one, which would be e to the negative 2 squared, so that would be 4, plus 2 times the next one, which would be e to the negative 5/2 squared, which would be that, plus 2 times the next one, which would be e to the negative 9 squared, plus 2 times the next one, which would be e to the negative 7/2 squared, which would be 49 over 4, plus 1 times the last one, which would be e to the negative 16. That will get you a 10 out of 10 on the exam. Okay, now if this was homework, They would actually expect you to put all those numbers into the calculator and then round it to maybe the nearest fourth decimal point. But on the exam, that is what you would do. Okay, any questions about any of this? Any questions about any of this? This section, okay, stop. This section is not, I repeat, not on the exam. Tomorrow, I have office hours today. Let me stop all this because it doesn't need to be on the recording.